Hey everybody, today we're going to be talking about quantum query complexity. The whole idea of query complexity, let me share my screen, is that basically what we would like to be able to do is we'd like to be able to kind of capture the computational power that quantum computers have. Now, if you recall, there's a lot of open questions about the power of quantum computing. And this, of course, is, kind of easily represented in terms of the hierarchy of different computational complexity classes. So the conjectured relationship between some of the popular computational complexity classes are as follows. BQP, and then out here, we've got p-space. And in each of these cases, basically the differences between each of these are potentially exponential, meaning inside each of the individual classes, we say that a problem is inside the complexity class BQP if it can be mapped using a polynomial size circuit to any other problem that we end up seeing inside the same class. Okay, but if we look at mapping a problem in BQP to a problem outside in p-space, the difference between these two problems could be potentially exponential. So this allows us to kind of get an idea of the qualitative differences in the cost of doing particular or solving particular problems on classical or quantum computers. And again, the class P, this is the set of decision problems that can be solved in polytime on a Turing machine. And so here, what I mean by polytime is that in terms of the size of the input, the number of ops needed to compute this function scales as order n to the alpha, where here, this is the number of bits in, and this over here is some constant greater than 0. Okay, now BPP, this is kind of the same, but non-deterministic Turing machines. So this basically is the class that we were taking a look at, or this class would encapsulate what we could do using probabilistic reversible computing, as we talked about in the beginning of the course. BQP, this is the set of decision problems that can be solved in poly n time on a quantum computer. Okay, and the final set of problems that we have here are the set of decision problems that can be solved in poly n space. Now, interestingly enough, this class over here is the only class inside the inside this hierarchy that I've drawn here that is explicitly quantum. P-space over here is a set that actually is inherently classical. So what this ends up saying is that if you're allowed exponential time, it turns out that you can actually simulate any quantum computer using a bounded amount of memory, or at least a polynomial size memory in the size of the inputs. And this is actually, it's really non-obvious, this inclusion of BQP inside p-space. And it technically has to do with these techniques called path integral methods. And so despite that, it may seem from this description, because of the fact that, worst case scenario, there is exponential separations between them. It might seem from this diagram that actually we've got a really good idea about how computational complexity goes. But in fact, we actually don't know. We don't know whether any of these boundaries are tight. So in particular, P could be a proper subset of BPP, or this could be exactly the same size. Same thing actually holds for BQP. BQP could be a proper superset of BPP, or it could actually be essentially the same size. And embarrassingly, we don't even know whether or not P is equal to P space. So in principle, even P space could collapse down to give everything being polynomially equivalent. So that's a real bummer. These hierarchies of computational time kind of qualitatively actually represent how powerful we expect quantum computers to be. But the problem is that it's very difficult for us to really reason whether or not these are tight inclusions. So query complexity is one way that we can approach these particular problems by restricting the way that the algorithms work. The idea basically is that assume you have a function. And this function, will map some series of input bits, n, to just 0 or 1. This over here is a Boolean function, and it can be thought of as a decision problem. So in particular, this function, acting on some input x, which we take to be an n-bit string, will either evaluate to yes, i.e. 1, or no, i.e. 0. Okay, and our task is to figure out, for some particular value of x, whether or not, the function evaluates to 0 or 1, ideally using a minimum number of gates. So the basic, the constraint, though, that we end up putting in query complexity is that we assume that the input to the problem can only be accessed by an oracle, named after, of course, the Oracle of Delphi. But the basic idea of the oracle is that what it does is it ends up holding x. So in this particular case, you can envision the following, that we've got a series of different bins over here. In this case, we've got n bits. The simplest such oracle would allow us to query a particular bit, anything we want, say the 0th bit going up to like the n minus first bit. And this oracle, I'll call it like O sub x, acting on a value I, will give the bit value x sub I. So for example, if we ended up having a bit string 0, 1, 1, 0, 1, and I wanted to call, and this is the value x, and I wanted to access the 3rd bit of it, I would call the oracle corresponding to it at value 2, which is, of course, the 3rd bit, assuming this one is the 0th bit. Okay, so OX equal 2 is equal to 1. So this is how query complexity ends up working. And so there's a lot of things that we can end up saying about query complexity pretty easily that are difficult for us to talk about more broadly. So in particular, here's an example. Let's take a look at a function called parity. Okay, and the idea of parity is that the function parity of some bit string say 0, 1, 0, 1, 1, 0, 1, is equal to the 1 if the number of ones is odd and 0 otherwise. Another way of more concretely putting it is that parity of some bit string B is equal to the sum over the individual bits in the bit string mod 2. Okay, so say we would like to figure this out, and our problem is the following: how many queries to a oracle that computes the bits of B, OB, are needed to compute parity of B. And I'm going to assume here with 0 error. So we demand that for every single input that the algorithm will compute the precise parity without fail. Okay, so let's actually figure this out. You know, and the way that we can prove that the number actually is equal to n queries is actually by contradiction. So assume that n minus 1 queries are needed. If n minus 1 queries are needed, and then without loss of generality, we can end up assuming that those queries are the first n minus 1 bits. So then we end up having this part of the string. We end up having B0 going all the way down to Bn minus 2, but we don't know Bn minus 1. Okay, so we have to give an output for this. Assume that sum over I, Bi is equal to, I don't know, let's call it C. Now, if we output C and Bn minus 1 is equal to 1, then we're wrong. Okay, then assume we output C plus 1 and Bn minus 1 is equal to 0, then wrong. And we see from this that in both cases, we have that the probability of guessing wrong equals 1/2, implies that n minus 1 queries are not sufficient. And similarly, it's easy to see that if n minus 1 queries aren't sufficient, that n minus 2 queries going all the way down will also not be sufficient, because we could always just throw away that information from those queries that we made to simulate a query with fewer ones. And so therefore, we end up needing, by contradiction, n queries, because obviously with n queries, we can just get the entire string and compute parity. So this is an example of a function where we can actually easily argue how many times we need to query this particular subroutine to compute the function. But the nice part about this is query complexity doesn't need to worry about details of the gate set. which is another great thing about it, because with that previous proof, we didn't need to have to worry about whether or not, we were using NAND gates, or whether or not we were using shifts of the head in a Turing machine. We just had to worry about the number of queries we made to these oracles. And this makes proving things a lot easier. And in fact, well, we don't know in terms of time complexity whether or not a non-deterministic Turing machine in BPP can polynomially simulate any quantum computer, i.e., we don't know whether or not there's a gap between these two complexity classes. There exist problems where super polynomial quantum speedups in query complexity exist. And so this is something that is really cool, because it provides us with some of the most solid evidence that we have so far that quantum computers actually are more powerful than classical. And so you might ask, all right, well, this is kind of an artificial construction, right? Like, what we really care about is the amount of time that it takes for a quantum computer to do it. And you've sidestepped this problem. You've taken a look at the problem of querying some subroutine. But actually, also, many of the problems that we look at in an everyday basis naturally have some kind of a useful subroutine. In fact, a subroutine that is often very, very expensive to compute. So here's a particular example for this. Let's say what we wanted to do is we wanted to try to break a crypto scheme. Now, this isn't the way that most crypto schemes are broken. Most of the time, they end up using another type of approach. But basically, if we wanted to consider breaking a crypto scheme, one of the things that we could do is we could envision having something like the following. We end up having like a password put in, which in the case of RSA could correspond to two different proposed factors that are used in the scheme. And so we could envision that we've got a subroutine that checks the password and outputs 0 or 1. And a naive algorithm would loop over this a whole bunch of times. Now, we wouldn't know necessarily how this works, because this checking a subroutine could just actually be like some website that's set up and ends up checking to see whether or not the password you've typed in actually is authentic or not. So we don't know necessarily how this works, but we're promised that it has this interface that when we input the password, it'll output 0 and 1. And so by taking a look at query complexity, it allows us to be able to build algorithms that use a common subroutine. So we can end up building this to crack any possible crypto scheme that ends up having this property, for example. Now, that is that's one of the big things about it, but also the query complexity in these sorts of settings ends up actually kind of being like time complexity if almost all compute takes place in the Oracle. So in this particular case, checking the individual passwords, this is something where likely most of the compute takes place even in a simple check. that ends up happening in the middle. The looping over all the possible passwords that we could guess for this, there's not very much time that we spend out there. But the vast majority of it is going to be checking that input to see whether or not it agrees with the output. So in this particular case, for example, the time needed to do that would be dominated by the time needed to query that subroutine. Another case that ends up coming up like this would be something like differential equation solvers. So the idea for a differential equation solver is that what you've got is we've got following sort of vector differential equation. We've got like x0 of t going down to x2 to the n minus 1 of t is equal to some matrix times x0 of t going down to x2 to the n minus 1 of t. So essentially, figuring out the derivatives of this matrix boil down to multiplying a matrix by this vector. And if we build an oracle that will take A and multiply it by an input vector, then this actually ends up often being like the main gating mechanism or the main thing that indicates the time complexity. So query to this oracle that either yields A or multiplies it by a vector will end up giving us a good surrogate for the amount of time that the overall DE solver ends up taking, because it'll spend almost all of its time implementing a query to this particular oracle. So this is one of the reasons why it's really nice in terms of structured alg design, because of the fact that you can just substitute in an oracle that you have for a particular case and change this over, for example, to solve a different differential equation by putting in a different matrix. We can do that immediately if we design our algorithms around oracles. But if we didn't do that, then we might have to go through and hand code it every single time for a different operator. So this is one of the reasons why it's really nice to work with oracles if you can help it. And the second is, of course, that time complexity is often comparable to the query complexity. Okay, wonderful. And so now the next question is, how do we think about queries in a quantum world? And so this ends up bringing up a wonderful topic of quantum oracles. So the simplest functions that transferring classical oracles over to quantum oracles actually isn't necessarily kind of obvious or unique. There's actually multiple correspondences between classical deterministic oracles and quantum oracles. The first type of quantum oracle that we can consider, which is most strongly analogous to this, is a type of oracle that we call a bit oracle. What a bit oracle does is it will take a input x and 0 in here, and then output x, 0, exclusive or function of x. Actually, it doesn't matter that it's 0. Under most circumstances, we'll assume that the output of the oracle here is stored in a register that's 0, but in general, it will be of this particular form. And so this is, we can view this as a reversible circuit that implements the function f of x. And here, this function f of x, for example, f of x could be the function that, for parity, stores our input bit string. So it would have, like x equals 0. We'd have 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0. So at x equals 0, it would give us the bit 0. At x equals 1, it would give us the bit 1, so on and so forth. Okay, so that's the notion of a bit oracle. The second is something that doesn't have a classical analog. And this example is what we call a phase oracle. And the way a phase oracle works is a phase oracle combined with some known constant omega that you choose beforehand will end up doing the following. It'll end up mapping x to e to the I omega f of x. So a phase oracle stores the value of the function in the phase of the input. All right, so there's some cases where actually in most quantum algorithms, one of the things that we'll find that if we're given a bit oracle, the most convenient thing to do is actually to convert it over to a phase oracle. However, it's not always easy, but it can be done in most cases to actually work backwards. So if you're given a phase oracle, it's often a lot more work to go backwards and end up building a bit oracle. But given a bit oracle, it's really easy to be able to build a phase oracle. Okay, so the third type of oracle, and this one actually does have a classical analog. This is what's called an amplitude oracle. Now, it doesn't have a deterministic classical analog, but the idea basically behind this is that we have x and 0, say, and x and 0 goes to x, or let's call it y, I guess, over here. And then it goes to say ry of 2 arc cosine f of x divided by the max over x, absolute value of f of x, y. Okay, so that was a little bit of a mouthful. Let me explain why that's the case. Recall that ry of 2 theta is equal to cosine theta identity plus I sine theta y. So as a particular example, let's imagine that we begin by querying our amplitude oracle on the state x at 0. This will map that to x ry of 2 arc cosine of f of x divided by max, absolute value of f of x, 0. Which, when we go through, this is equal to x times cosine of arc cosine of f of x over the maximum value of absolute value of f of x, 0, plus sine of arc cosine of 1. Which is equal to, because the cosine and the arc cosine cancel, this is equal to x f of x divided by max f of x. And then using some trig identities, or equivalently seeing that the tensor product has to be a unit vector, we can end up seeing that this is going to be equal to plus it's going to be equal to, I guess, actually minus square root of 1 minus f of x squared divided by max, absolute value of f of x, 1. All right, so this ends up actually now giving our function value as an amplitude over here. That's why we call it an amplitude oracle. And so the big thing about it is that, well, the phase oracle only made sense in the quantum setting. The amplitude oracle actually also makes sense in the classical setting, because we could envision a situation where we have EX and 0, tensor E0, for just 2-bit strings. If we put this into a probabilistic classical computer, then we could end up building the probability distribution, f of x divided by max f of x E0 plus 1 minus f of x over max f of x times E1. And so you can see that this has a probabilistic classical analog, but it isn't deterministic. So we'll spend most of our time talking about a bit and phase oracles. However, as we end up getting to the Harrow-Hassett-Lloyd algorithm, which will come later, then we will see that actually amplitude oracles are a really natural way of representing these types of problems. So the last thing that I want to talk about is how the equivalence between the oracles ends up going. And so first thing is equivalence between them. So first thing that I'd like to be able to do is I'd like to be able to say, one, let f map 0, 1 to the n to 0, 1. And we're going to take omega is equal to pi. Then OF, the oracle corresponding to this of x, will be equal to just -1 to the f of x, x. And let's call it O bar of f of x 0 equal x f of x. This is an example of a bit oracle, and this is an example of a phase oracle. We have that the claim is I guess a constant number of queries to OF bar can simulate a query to the phase oracle OF. And this is how we can do it. So let's begin by preparing a state X up here and 0 down there. We're going to then apply a NOT gate to 0, and then we're going to apply a Hadamard transform here. Then after we do this, we are going to apply OF bar to apply the bit oracle to the bottom. Now, when we've done that, what we're going to do is, well, actually, let's just work out this part first. So going through it, we have x0 with the NOT gate. This is going to map to x, then 1. Now we apply the Hadamard, and this is going to map to x over root 2, 0, actually -1. And then once we query OF, what this will map to is x over root 2 f of x minus 1 exclusive or f of x. And this, we can see, is equal to -1 to the x over root 2, 0 minus 1. Now, why do I say that? Well, -1 to the f of x. Let's say f of x is equal to 0. Well, if f of x is equal to 0, then we have that these two expressions are exactly the same. If f of x is equal to 1, on the other hand, then this is 1, and that's 0. And this is equal to minus 0 minus 1. And so I just take this minus sign here and put it out in front. And we can see that these two equations match. So then this will give us minus 1 to the f of x, tensored with this stuff back here that we don't want. Well, we can fix that just by applying a Hadamard gate. This Hadamard gate will map the state to -1 to the f of x, times 1. And now we put it through another NOT gate. And this will just go to -1 to the f of x, 0. And there you have it. This trick of taking the negative sign from the ancilla and moving it out here, which we can always do, right? Because the sign is a constant. And constants, they can move around any way you want when you order them against matrices. This trick of rewriting the phase so that it's in front of the first qubit rather than the last one is known as the phase kickback effect. Another way of thinking about it is that the signs that are generated inside your quantum circuit, or the phases, are never associated with just one of the systems, and you can move it anywhere you feel like, and the two are logically equivalent. Like, for example, let's say we had -xy. This is equal to x -y. And this simple observation is, again, given a complex name in quantum computing, we call this the phase kickback effect. But it's really just this obvious fact of the tensor product, that negative signs distribute over tensor products. Okay, so that shows that a single query to a bit oracle can be used in order to simulate a query to a phase oracle. But what about the converse? It turns out the converse isn't quite directly true. The closest converse that we can end up getting is that one query to controlled controlled OF can implement one query to O bar F. So this is the bit oracle. So the phase oracles, as we alluded to before, phase oracles actually aren't quite as powerful as the bit oracle. But if we have a controlled version of the phase oracle, we can actually interconvert back. And so what I mean by a controlled version of OF is the following. Let's imagine that I've got a state A up here. This is just a single qubit space, and I've got X down here. A controlled query will end up working as follows. This would be OF, and then the result that we'll get back out will be A E to the I pi F of X A X. So what do I mean by this? If A equals 0, then what happens is we multiply these two. And if A is 0, then this phase is always going to be 1. So nothing will happen whatsoever if A is 0. If A, on the other hand, is 1, then what ends up happening is a gate actually will do something. And we will end up getting a phase of -1 to the f of x, which is equal to, of course, e to the I pi f of x, because e to the I pi is equal to -1. Okay, So that is how we can end up building a controlled query to it. So now let's go through and ask how we can implement the bit oracle from this. The bit oracle actually can be implemented by the following. Let's say we begin with 0 over here, and we have our state x down here. Now, the very first thing that we're going to do, just like we do in almost every quantum algorithm, is we're going to hit it with a Hadamard. Why is that? Well, at a high level, the Hadamard, what ends up converting between phase and bits. Like, for example, we have that HZH is equal to X. And so if we look at Z, that's 1, -1, 0, 0. And this gets mapped to X, which is 0, 1, 0 over here. So these two matrices contain, in some sense, exactly the same information, but the information for Z is stored in these phases. However, for X, this information is stored in the bit values. And Hadamard allows us to interchange between the two. So then it stands to reason that this circuit probably is exactly what we need, but let's go through and verify. So the very first thing is we get 0 plus 1 over square root 2 tensored with X from the Hadamard. And now this, under the controlled operation, ends up going to 0 X plus 1 times -1 to the f of x, x over root 2. Now the Hadamard, in the end, it will now end up causing us to go to 0 times what? Yes, it'll go to 0, 1 plus -1 to the f of x, x over 2 plus 1 of 1 minus -1 to the f of x, x divided by 2. Okay, cool. So -1 to the f of x. So, okay, let's just consider a truth table here. Here's a value of f of x, and now we're going to do 1 plus -1 to the f of x divided by 2. So if f of x is 0 over here, because again, it's a Boolean function, then we have that this is 1 plus 1 over 2 equals 1. And if we have it's 1, then what we end up getting is we end up getting that this is 1 minus 1 over 2 is equal to 0. So if this is 0, then this will give us 0 x if f of x equals 0. But now let's ask the question, well, what about 1 minus -1 to the f of x divided by 2? Well, in this case, we would get 1 minus 1 over 2 equals 0. And unsurprisingly, we get 1 plus 1 over 2, which is equal to not 2, it's equal to 1. So we end up seeing that in this case, if f of x is 1, and we're looking at this coefficient, then that is going to evaluate to 1. So this will end up meaning that the following state ends up holding, that we end up getting that, which is, of course, equal to the exact same result that we would get by feeding 0 and x into our bit oracle. So this ends up showing that both of these types of oracles, or at least special cases, that can be interconverted under the assumption that we're able to build a controlled version of the oracles. But in general, the the bit oracle is a more powerful oracle than the phase oracle. And so a rule of thumb that's good to follow when you're building your own quantum algorithms is to use as simple of an oracle as you possibly can. So in particular, if a phase oracle will allow you to solve your particular problem, it's usually best to postulate that your quantum algorithm uses a phase oracle, because we can always simulate a query to a phase oracle using a bit oracle. However, if you posit for your algorithm that you need a bit oracle, but in reality, you only actually needed a phase oracle, then that can often confuse folks who come around and try to use your idea, because they have to figure out how to work backwards. And it's not always possible to work backwards, but you can in some cases. And so for that reason, it's appropriate, it's important to pick the right tool for the job. And picking amongst these three analogs of what a classical oracle, or at least a classical deterministic oracle, would end up looking like is really important in order to squeeze the most out of your algorithms. And so we're going to see a little bit of these decisions next time when we talk about the Bernstein-Vazirani algorithm, which actually was the first algorithm that was ever discovered that affords a super polynomial advantage over actually the best possible classical algorithms for computing the value of a hidden string. So thanks a lot, and see you all next time.